Sir Kannan Gopalakrishnan. He was working as a senior architect at Engineering Design Research Centre, L&T Construction, India's largest construction company. He's also worked on projects ranging from institutional buildings to international airports, apartment complexes to aircraft hangars. He's also attended 3 international conferences and 2 national conferences, and has also presented technical papers at the Jawaharlal Nehru University, Delhi, and the MSRIT, Bangalore. He's also won the national championship at Archaman at the India's largest architecture quiz. Sir Kannan Gopalakrishnan currently runs a design firm, Habitat Design Studio, and he is also a visiting faculty at the renowned architecture schools in Tamil Nadu.
Welcome to UGC lecture series. This is the lecture number 2 of the lecture series Structures and Architecture. In this unit, we will be continuing the unit 1, whereas in the previous video, we saw the importance of structures in construction. We saw how the concept of structures came into existence and how it evolved over time. We also saw about rock cut architecture, monolithic architecture, neolithic architecture and trebated structures. Now, in this series, we will be looking at birth of arches, arcuate constructions, vault and vaulting systems, buttresses and flying buttresses. Let us move on to arches. If you look at arches, this is an example of a natural looking arch which exists naturally in the world, but we are not going to look at these arches in our subject today. We are going to look at man-made arches which has a very systemic sense of how the load is transferred from one point to another point. By definition, arch is a curved structure that spans a space and it may or may not have load supporting on top of that. If you look at an arch and see how it works, it is a purely compression form of a structural member, which means that the amount of tensile stresses that the structure is carrying is 0. Every load that the structure is carrying is purely a compressive force. Here, if you could see, it can span a very large area by resolving forces into completely compressive stresses, in turn eliminating tensile stresses. This is sometimes referred to as the arch action. If you look at a normal compressive strength, which we saw in a previous episode, a post and lintel fashion. If you could see the post, how the load transfers in a post is, on the top surface of the post, there is a compressive stress acting on the post, whereas in the bottom surface of the post, there is always a tensile stress acting on the post. A tensile stress is nothing but a pulling force, whereas a compressive stress is a pushing force. In arches, the beauty of an arch is it is entirely of a compressive stress nature. There is absolutely no tensile stresses involved. This is a loading pattern. In an arch, typically the load comes from the top and the load gets bifurcated onto either sides and they are carried through the bricks or the stones or any material that is placed in between, and it is carried towards the supports. When the arch carries the load, there are 2 components that the load is split into. One is the vertical component and another one is the horizontal component. The vertical component is a purely compressive strength and the horizontal component is also a compressive strength, but it is called a lateral thrust. To explain how lateral thrust works, let us construct the arch first and then let us assume that the arch is carrying more load than it is designed for. In case when the arch is carrying more load than it is designed for, if you look at the picture on the bottom left corner, we will see that the arch buckles under its own weight, which means that there is too much of force acting on the arch, and when the lateral forces are more than what the arch can carry, there is a horizontal splay which the arch creates, which means the supporting members go outward, which means that the arch caves in on its own. The arch is a self-supporting structure otherwise, which in this case it is not a self-supporting structure. The weight of the arch itself and the weight acting on top of it makes the arch splay outside and the thrust defeats the arch purpose. Interestingly, arches have been in the construction industry for quite some time now. It was first discovered by the Mesopotamians. They were using brick construction. It was as early as 2nd millennium BC. The Greeks also knew how to construct with arches. They did a lot of underground structures, but most of the Greek construction using arches were confined to underground structures. But it was the Romans who used the arches for its fullest potential. They used the arches for practically every kind of building that they constructed: palaces, temples, malls, big complexes, sports arenas. Any public building, they had an arch. They even constructed kilometers and miles long aqueducts which carry water from the source to the city, and they constructed it entirely of arch members. Like the Roman arch itself is a semicircular arch. If you look at these pictures here, this is the triumph of the arch under the Roman architecture. The heights of Roman architecture can be seen through these pictures, where you can see a large span of structures, large span, entire road, entire rivers being spanned just by the arches, and how the arches are being constructed. They used materials like brick, they used concrete, they used stone, and in each of these materials they were able to express the structural integrity of the arch through the material. These are famous buildings which you can see in almost every Roman city. The buildings are designed for one practical purpose. They have games and sports conducted inside these buildings. The one on the left is the Colosseum, one on the right is from the other Roman cities, where you can find numerous series of arches stacked on top of each other, forming 3-storied, 4-storied buildings of completely arched construction. And these buildings stand the test of time even after 2000 years now. Now let us go and see how an arch works, or how a loading on an arch happens. Every element inside an arch has to have a right place and a right job to do it. Each element, let us come to the elements later, but then every element has a place and a job to do in an arch. They cannot be in a wrong place and or do the wrong job. If you see the top right picture, there are series of stones which are arranged in this place also. There are a series of stones which are arranged in this fashion also. The main difference between the one on the left and the one on the right picture is how the stones are arranged. If you could see clearly, all the stones are placed in such a way that the load of one stone is easily transferable to the other stone purely by compression, whereas in this picture, load of one stone is neither transferred to another stone or it is absorbed completely by the ground. So, this stone and this stone here, all these individual stones are left individual. They do not correspond to any complex system, which means that they can buckle and fall under their own weight. This is a typically wrong way to how an arch is constructed, whereas this is a way an arch needs to be constructed. And especially when you apply load onto an arch, you have to be very careful, because the load has to be applied directly at the middle or on top of the keystone. If the load does not act on the middle, what happens is, well, you can see in the picture in the bottom left corner. Here the load applies onto this stone, which means that these stones on this side cave inside, whereas creating an upward thrust on this area, thereby dislocating the entire shape and structural integrity of the arch itself. Any load which is acting other than on the keystone area is not a proper loading pattern for an arch. The loading pattern needs to be very precise and very calculatable. Let's move on and talk about the different parts of an arch. We have studied parts of an arch in junior classes, even in our first and second years, but then we will quickly brush through the parts of an arch once again, so that we will understand how the arch works better way. An arch typically stands on either an impost or a wall or posts, which are located in these areas. The first stone on which an entire arch is built, first stone on this side and on this side, these stones are called the springer stones. The other stones which are kept on top of the springer stones are called voussoirs. The stones on either side, this side and this side, both the sides, they are called voussoirs. And the entire assembly of the stones from here till the near top area is called the haunch, whereas the stone which is placed right in the middle on top is called the keystone. The upper side of the arch is called the extradose and the inner surface of the arch is called the intradose. There is a line that connects the 2 points where the arch begins, this point here and this point here. This line is called the springing line. We need to know this, as in the next slide we will be looking at different types of arches, and most of these type of arches have one of these properties varying. So, we need to be conversant with the terminology right here. Moving on to the different types of arches, I have numerous types of arches on the screen here, and can you identify as to which type each of these belongs to? Let me get through it. The first arch here is called a semicircular arch. It is called semicircular arch because the distance between the two springing points is covered by an exact semicircle, and from the center point of the springer line, the distance of the arch is equal to at any point of the arch. That is why it is called semicircular arch. If you look at the second arch here, this is also a type of semicircular arch, but we can see slight difference from the one. The similarity is at any point on the arch, the distance from the center is the same, just like the semicircular arch, but then it is entirely not a semicircle because the center of the arch is below the springing line. The springing line is right here and the center of the arch is below the springing line, which means the resulting part of the circle is not a semicircle, but a segment, hence the name segmental arch. Moving on to the third arch, this arch has not one center like in the previous two arches, but this has two centers. The two centers are not on the springing points, not on the center of the arch itself, but at equal distances from the springing points. This arrangement results in a type of curve which we are very comfortable and which we very well know with. This curve is called an ellipse. An ellipse always has two centers, and since it is a half ellipse, it is called as elliptical arch. Moving on to the next part, here this arch is very similar to the first and second type of arches. Again, the distance between any point on the arch to the center of the arch is the same, but the only difference between these arches and the fourth arch is the point, the center point of the arch is above the springing line. This is the springing line right here, and the center point is above the springing line, which means that this entire arch is standing on top of something called a stilt, hence the name stilted arch. Arches 5 and 6 have something very common, which is unique of these two arches, which no other arch types have. These are the only type of arches where the size of the arch is bigger than the springing line itself, and due to their unique shape, they are called horseshoe arches. They are called horseshoe arches because they resemble a horseshoe, very simple as that. And why are they two different types? The first one is called a round horseshoe arch and the second one is called a pointed horseshoe arch. Let us move on to arches 7, 8 and 9. In a simpler, very simple layman terms, arches 7, 8 and 9 can be called as pointed arches. But then we are not laymen, are we? We are architects. We need to define them by their clear, exact architectural name. Let us go on to arch number 7. If you look at it, this arch is made up of two arcs of a circle whose centers are here and here. If you look at it carefully, the center of the arcs are outside the springing points. These are the springing points. The centers of the arcs are outside the springing points, and hence this arch is called a lancet arch. Arch number 8 is where the centers of the two arcs which form the arches are exactly on top of the springing points. This is called an equilateral arch, whereas in arch number 9, it is the same pointed arch. Center of the arcs which give the arches are located inside the springing point within the arch springing line. This type of an arch is called a drop arch. Moving on to a little more further complicated types of arches, arch number 10, 11 and 12 are more complicated than their siblings, the other 9. If you look at arch number 10, you can see that they do not have one or two centers like the previous arches, they have 4 centers, and if you could see them carefully, they form different cusps within the arch itself, hence they are called a cusp arch. In this case, since there are like 1, 2 and 3 lines, they are also called as a trifoliate arch. Moving on to the next arch, arch number 11 has the centers not only on the inside, but also on the outside of the arch as well. This arch is called the OG arch, but a more common name for this OG arch is a Mughal arch, because it was the Mughals who used this arch so often that the name itself is synonymous with their reign. Moving on to the 12th arch, it is a 4-centered arch, typically because the arch itself is made of 4 centers, 1, 2, 3 and 4 here, and this arch is very similar to the drop arch, but then the drop is not that high, is a very shallow kind of an arch. Sometimes this arch is also called as a Tudor arch. Let us move on to a topic where we talk about the structural advantages of different kinds of arches. Why do we have so many types of arches? Wouldn't just one arch typology be sufficient to construct all our buildings? Why do we need so many arches? Well, 2 reasons. Reason number 1 is because we don't want to look at the same thing over and over and over again. We want to see different things. Reason number 2 is different arches have different structural abilities and different arches behave in a different structural way. Let us look at typically one such type, which is a pointed arch. We all know that the loading pattern of an arch works like this. The load comes from the top, from the keystone it gets distributed on either side, and then while it comes down, the load typically has a vertical component and a horizontal component. Let us take the case of this pointed arch. Here this M1 and M2 are the 2 springing points. These R1s and R2s are the lines from which the arch is drawn. This arch number 2 is an equilateral arch, whereas arch number 1 is a slightly more pointed arch, arch number 3 is a less pointed arch. If we could clearly map the structural components of this particular arches, we know that there is a vertical component of the arch which goes directly through M1 and M2, and there is also a horizontal component of these arches which goes away from M1 and M2 inside the piers or the columns where it is supported on. These loads are lateral forces, which we know. If you could compare these 1, 2 and 3 arches, arch number 1, because of its height, has more of a vertical component and less of horizontal component, whereas arch number 3 has less of vertical component, has more of horizontal component. Structurally, we prefer arch number 1 because it takes care of vertical loading very easily and it gives very less room for horizontal loads. If the horizontal loads are reduced, the main advantage that you get is you do not have to provide a big thick column or a pier. You can reduce the thickness of the pier column. If the thickness of the column and pier is reduced, which means that your overall loading comes down. If your overall loading comes down, you can build taller, you can build higher, and you can go for very large, huge, dramatic structures. This is the reason why all the Gothic churches or Gothic cathedrals have pointed arches in comparison with Romanesque architecture, where all the arches are semicircle. In Romanesque cathedrals, the height is not given much importance, whereas in Gothic cathedrals, they go for an enormous amount of height. The verticality is a main element in Gothic architecture. One thing which clearly got them the verticality is the pointed arch. That such is the structural advantage of a pointed arch or a tall arch rather than a short arch. Let us move on to another subject called vaulting. What is a vault? Let us define the vault in a very simple terms. We will talk about one barrel vault, which is the basic of all the vaults. It is defined in this way. Vault is an architectural term for an arched form used to provide a space with a ceiling or a roof. Here, this is an arch. We know that. This is the face of an arch. When the face of an arch is extruded, it becomes a vault. You have an arch, you extrude the arch along the face of the arch. It forms a barrel vault. This barrel vault is also called as a tunnel vault or a wagon vault. It is called a tunnel vault because it is mostly used in tunnels, under the earth structures, below ground structures. The best part about barrel vault is when it is used below the ground, you don't have to have any additional structural support, as the earth on either side of it takes care of all the lateral loads. But when in this arch, when this barrel vault is used above ground, you need to provide additional support on either sides to take care of the loading. The loading pattern on the vault is very similar to an arch. We know that in an arch, when the load comes on top, it gets transferred onto the sides, and typically there is a vertical component and there is a horizontal lateral weight component. The same principle is what applies in a vault also. The load is carried by all the Osier stones on the sides, and again typically there is a vertical component, the main compressive load, and then there is a lateral weight component which occurs on the sides. This is again a thrust. This is when I told you about underground structures. When the vault is being constructed underground, the weight of the earth on the surrounding areas, these loads counteract all these loads so that the vault is in shape. Whereas, when it happens on above ground, you need to counteract these forces by some other structures. We will be dealing with one or two of those structures in the later stages, but just remember for the time being that these horizontal forces are to be considered while designing. Let us move on to the next type of arch, which is called the groin vault, which is a little bit more complicated than the previous arch, which is called the barrel vault. Groin vault typically results when two barrel vaults here meet. This is one barrel vault, this is another barrel vault. They both have the same radius, they both have the same distances. When these two meet perpendicularly, this is how it looks from underneath, and this is what results. This is called a groin vault. If a series of two or more barrel vaults intersect at one another, the load which is transferred to the columns or the piers happens on the intersection areas, and the thrust is transmitted to the outer cross walls. Let us move on to a little more complicated vaulting system, which is called the ribbed vault. A ribbed vault system is very similar to a normal groin vault, but then the only difference between the groin vault and the ribbed vault is wherever you have these joints are reinforced by ribs. Here you go, these A, C, B, these are called ribs. Wherever you have an intersection of these lines, arches, you have something called ribs. It is called a six-partite vaulting because there are 6 ribs which meet in a particular unit of a vaulting system. Let us take an example of this particular system, where you see 1, 2, 3 ribs arising from this side and 3 ribs arising from this side. In this unit, there are totally 6 ribs. So, this is called a six-partite vaulting system. A further more complicated vaulting system is called the fan vault. A fan vault results in a very beautiful vaulting system, and it gives a very pleasant look. Most of the Gothic cathedrals, later Gothic cathedrals, use the fan vaulting system. The reason why the name fan vault, you might have all easily guessed, because of the shape. It looks like a fan. Look at the picture. It looks like a fan, typically like a hand fan. So, hence the name fan vaulting. These fan vaults are much more complicated systems of vaulting than the previous groin vaults or the barrel vaults or even the ribbed vaults. These are much higher levels of vaulting, and clearly you can trace the evolution from barrel vault to a groin vault to a ribbed vault and now to a fan vaulting system. Now, let us move on to the next interesting topic, which is a dome. This picture which you see here is the dome of a building called Pantheon in Rome, where the height of the dome architecture in Roman times is achieved here. If you could clearly see the dome, in section all you see is an arch. This dome is very big, which you would have probably realized because of the scale which is given below. This dome diameter is more than 40 meters, and there is an oculus on top which is 11 meters approximately in diameter. We all know this data, but what we did not know was the reason why there was a big oculus right in the middle of the dome. Early Romans say that the oculus is a means through which the men can pray to the gods directly. Through the oculus they can look at the skies, and through the skies they can look at their gods and they can take the blessings of the gods directly. Oculus typically means eye. Oculus of the dome is usually referred to oculus of the god itself, which means it's even called in some places the eye of the god. But then what really happened in this place is, if you could see this diameter of the top area oculus is, like I said, approximately 11 meters. Just like in an arch construction, the topmost point is something called a keystone, where you put the keystone and lock everything into place. While they construct an arch, what they do is they make a frame, it's called a centering, and then the centering needs to be in place until the keystone is placed on the top. The moment the keystone is placed on the top and the arch is locked, you can immediately take the centering off, because the arch then becomes a completely self-supporting structure. Since a dome is an arch which is rotated onto 360 degrees onto its axis, a dome works on typically the same principles. But since the dome is spherical, a semi-sphere, keystone is not a two-dimensional structure anymore, but it is a giant 3D circle which has a small tilt on the top. This small tilt, this giant thing needs to be placed right on the top, where if you could see this picture, you need a circular big large element of this size to be kept on top of these two areas. And remember that the diameter of this entire place is close to 11 meters, and this cannot fall down inside the temple at any point. So how do you place that? That was a serious question which the Romans faced at that particular point of time. And since they couldn't find an answer, that is the reason why the Pantheon does not have a top. That is the reason why Pantheon has an oculus right in the middle. The reason is not a spiritual symbolic element, the reason is a simple structural inability by the Romans. These domes have very contrasting features compared to modern day domes. This dome here was made of concrete and it was reinforced by hay, by used by all natural materials. The reason why you see these square boxes right here are because the amount of concrete which is used to make this dome was very high, and they wanted to reduce the amount of concrete. So, they made these square designs so that the amount of concrete can be reduced by a little bit, which can save on their cost. So, but the domes which we make nowadays are much more complicated and much more interesting, because today we have the advent of shell technology. We can calculate mathematical equations to a very precise number. Today's hyperbolic paraboloid structures, hyperbolic structures are much more common today than it was in the previous day. If you could look at these pictures, these are modern day arches. From these you can see that the advancement which we have had in the field of arches, in the field of geodesic domes, are much more prominent than in any other fields. So, this is a reason why domes and arches are still being studied by structural engineers and architects around the world, even today, even after 2000, 3000 years of its discovery. Now, we will move on to our final part of this particular lecture, which is buttresses and flying buttresses. What is a buttress? If you look at the picture, in this picture there is a load of the water coming on from one side, and then the wall which retains this liquid on one side, and to counteract the load of the water you need these triangle looking structures, so that their loading can counteract the load of the water. These triangle looking structures are buttresses. Now, let us define a buttress. Buttress is an architectural structure built against or projecting from a wall which serves to support or reinforce the wall itself. If you do not think you have seen buttresses in day-to-day life, think again, look at these pictures. I am very sure you have seen buttresses in day-to-day life. This is a dam. The wall right in the middle needs to take the load of the entire water that it retains. Since the wall cannot do this job alone, we have these helping structures to take the lateral loads. Same is the case with this dam. And if you think that the buttresses are restricted only to dams? Think again. If any wall is going to fall, or if there is too much of loading onto a single wall, you can find these buttresses. You can find buttresses very commonly in forts, in big palace buildings where the walls are huge, thick. Just to retain the wall itself is a big task there. So, they provide what is called a buttress to support the load of the wall. Let us look at another interesting thing called the flying buttresses. Flying buttresses are typically buttresses, but there is a very small difference. What does a buttress do? It takes the load from a wall and it transports to the ground. That is what a flying buttress also does. But then the way that the flying buttress works is slightly different. When a buttress is completely attached to a wall at all points from the starting point till the ground level, the buttress is attached, whereas a flying buttress is not attached at all points. It is attached only at one point. If you look at the picture on the left here, this person right here is being supported by these two people, and if you could see, the load of this person is being taken by these two people. In this case, there is no loading acting on the person from the wall, but then a flying buttress typically takes load which transfers through the flying buttress, it reaches down through the piers. Look at the pictures on the right. This here, the load of the pier is too immense because there is loading coming from the top. The top of the truss provides immense loading onto the piers, but then the pier cannot take the load alone. So, a part of the load is being transferred to these sub piers, which are connected by the main piers by means of a flying buttress. Same is the case with these areas. Let us see the difference between a buttress and a flying buttress. If you could see this picture, here these two are the main piers that take the load of the main structure. We know that an arch or a vault gives horizontal thrusts as well as vertical loads. Vertical loads can easily be taken care of by the piers themselves, but the lateral loads is what we have to worry about. These lateral loads can be very dangerous because once the lateral load goes beyond a certain limit, we saw how a thrust acts in an arch, right? The arch splays out and it buckles under. So, everything caves in. That cannot happen to our buildings. So, what we do here is we either build an abutment or a buttress on one side where the entire structure is being supported by the structure on the one side, or we build something called a flying buttress where a part of the load is taken care of through these members called the flyers, and then they transfer the load to smaller piers which are on either sides. So, this is the main difference between a buttress and a flying buttress. Here are some pictures of a flying buttresses where you can see cathedrals across Europe, from Italy to France to England to Germany. You can see cathedrals everywhere sporting these flying buttresses. Sometimes the number of flying buttresses can be even 3, not just 1 in this case, maybe 3 in this case. We almost come to the close of this lecture, and let us quickly see what we have learnt in this particular lecture. We understood the history and importance of arches in construction. We saw different parts of an arch, how arches have sculpted the history of architecture. We saw how an arch is extended to different other variations, especially the vault and the dome. We studied the different types of vaults, different types of domes and how they work, and we even talked about a case of Pantheon. We saw how to calculate and counteract the lateral loads due to arch action. We typically saw buttresses and flying buttresses and how they are helping us in counteracting the loads, especially the lateral loads which are acting on an arch. Now, these are some questions which you can answer based on the expertise which you have just achieved by the lecture. Explain the structural importance of arch in architecture, trace its history through different styles. What are the different types of arch? Explain with relevant sketches and examples. How do vaults differ from arches? Where are they used? Explain dome construction. Trace the importance of dome through history and explain why it is relevant to study domes even today. Chalk out the differences between buttresses and flying buttresses with relevant sketches. On the next lecture series, we will be looking at cathedrals and spires. We will be looking at tents and masted structures. We will be looking at bridges through history, how bridges worked in history and how modern bridges work, and how we have redefined the way we think about bridges throughout history. We will be looking at these things in the next upcoming series. Thank you.